Hello Year 13 chemists, welcome to TP's Chemistry Cuts. In this clip we calculate the pH of a buffer that's been prepared by partially neutralising a weak acid with a strong base.
Right, okay, so I'll start again. So far we've looked at what buffers are and general properties of them, and today we're going to do some true calculations involving buffers, and these are challenging. There's many steps that bring together quite a few ideas, okay? So you need to be well focused on this. So if we consider a weak acid as our example, so I'm going to use HF, hydrofluoric acid, and if we partially neutralise that with something like sodium hydroxide, first thing to say, notice how I've left out the sodium plus, because that's the unreactive part of the strong base, the conjugate acid of it that's going to be on the other side. It doesn't do anything, it's a spectator, so we can forget it. Okay? So you're taking the weak acid and you're neutralising it with a strong base, which is equivalent to adding OH minus to it, and you're forming its conjugate base. If we stop part way though, don't go completely to the end point of the neutralisation, but only go part way, then we'll end up with a mixture of the weak acid and its conjugate base. And that's one way, it's the simplest way of preparing a buffer. That's the idea behind it. Let's have a look at how we would calculate a pH of a buffer that we form by partial neutralisation. So this is a fairly typical type of question where you might have two different volumes and two different concentrations, and you've gone part way to neutralising it. So the first thing is to be aware of the type of buffer that's involved. It's HF with its conjugate base fluoride. Okay? And I've given you the data, all the data that you need. So you need a Ka value for anything to do with a weak acid or weak base. You need a Ka value, and you will be given this equation. Okay, and interestingly enough, that along with the calculation of a pH, so maybe I should add that in, are the only things you need. Okay, so what would be the first thing I'm going to do? What do I always start off by doing? Which equation?
Neutralization.
Neutralization one. Just the dissociation of the weak acid in water. Let's start off with that, because we've been given a Ka, so why don't we write out, first of all, the reaction equation, and then the expression for Ka for that reaction. So we've got HF in water, and we form the conjugate base F minus in small quantities plus H3o plus, and Ka for this is equal to the concentration of F minus times H3o plus over HF. Now what we're ultimately needing to do is to calculate the pH. So we're going to need to rearrange this equation so that the subject of the equation, the thing that we need to put on the left hand side, is the concentration of H3o plus, because that's what we get the pH from. Yeah? So let's do that now. So if I put so, concentration of H3o plus, and it's a simple case of cross multiplying, so HF goes up, and then F minus comes down. So let's have a look at this equation and see what we've got and see what we haven't yet got that need to work out. So we actually have that because that's given here. Okay, but we don't yet have these two. So we need to get hold of those, because what we've got are concentrations before the reaction started, the neutralisation reaction started, or partial neutralisation What we need to do is to work out their concentrations once we've stopped partially neutralising it and we've got our finish, our end mixture. So that's where this comes in. But first of all, let's just rewrite out the neutralisation reaction equation so that we can see how we're going to work out the final concentrations. So, HF Q plus OH minus AQ, and with every neutralisation reaction, one-way arrow as opposed to the reverse arrow for the weak acid in water, which is not a neutralisation reaction. Okay, so we've got F minus plus H2O. Now, what we're going to need is when we're looking at an equation, we're always looking at moles reacting together. Okay, and we're going to need to know how many moles we're actually going to be reacting together at the start of the reaction, so we can work out what's left when we've partially neutralised it. Okay, and you'll see what I mean in a minute. Okay, and so this is where this comes in. Okay, that rearranges to N. Okay, so we've got that. And what we need to do before we can start working out what we've got at the end of the reaction is we need to work out the amounts in solution at the point when we mix them and do the partial neutralisation. Okay, so if we look at first of all the amount of HF, well, the concentration of HF is 0.25 moles per litre, and the volume is 50 mils. Okay. Somebody quickly calculate that for me, please. Okay. Now, the number of moles of OH minus, again, C times V, and we've got 0.15 times 40 over 1,000. Somebody can quickly calculate that one for me. Okay. Now, what do we do with these? Now, what you can see is, first of all, this number is bigger than that. Yeah? So we've got more acid than base. So when we react away the acid, there's going to be some left over when all the base is used up. That's what that's telling us. Yeah? So let's do a simple bit of maths, shall we, to see how this works. If I had 50 molecules of that, and say 20 molecules of OH minus at the beginning, how many molecules of OH minus am I going to get at the end? None, because it's all going to react away. So I'll put a dash there. Sorry, I'm going to take away 20 of that. Sorry, so if I'm reacting 20 of this with it, I'm going to lose 20 from there. But I'm going to have 30 left over. Does that make sense? And when I take 20 off that, it's going to make this. So I'm going to get 20 of these. Yeah? So the 50 I had here, 30 are left over, and 20 have gone over to here. Because they've had the OH minus remove the H from it. Does that make sense? So I'll start it again. I've got 20 OH minuses. They're going to take away H plus from 20 of those. So I'll have 30 left. So when I take away 20 H pluses from there, I'm going to get 20 F minuses. F minuses, yeah? If we want the concentration of HF, this is before the reaction. Okay? So this is before. After, okay, the concentration, or the number of moles, number of moles of HF is equal to the number of moles HF before minus the number of moles of OH minus. That's what we've just said, isn't it? We've just taken the number of moles of OH minus away from the number of moles of HF. And that is equal to 1.25 times 10 to the minus 2 minus 6.00 times 10 to the minus 3, which is equal to 6.50 times 10 to the minus 3. Yeah? So I started off with 50 of these. Yeah? 50 HF molecules. Yeah? And I added 20 OH minuses, which are going to remove H from 20. Because it's a one-to-one reaction, yeah?
Yes.
So if I had 50, how much am I going to end up with?
30.
30. So in other words, what I've done, I've taken this amount, I've taken that amount from that.
Oh, because OH minus has reacted with HF, it's taken away some of the HF.
But we haven't got enough to break all of them.
Yeah.
So we're working out what's left over.
Gotcha.
Yeah? So I've got 50 minus 20 gave me 30. Those 20 that have been lost have now formed F minuses. So I've got 20 here. So in other words, the number I've got here is the concentration of OH minus.
Yeah.
The concentration I get, or the number I get here, is the number of HF in the original mixture minus the OH minus, which is what I'm doing now. Does that make sense? Okay. And so the number of moles of F minus is equal to the number of moles of OH minus, which is equal to 6.00 times 10 to the minus 3. Okay? So it's a relatively straightforward procedure when you've done this a few times. So you work out the amount of the weak acid, you work out the amount of the strong base, you subtract the strong base away from the weak acid, and that gives you the amount of weak acid left, and the amount of the strong base is actually the amount of the conjugate base that you form. Okay? So now we've got those two amounts, we need to convert them into a concentration. And this is where you've got to be very, very careful. Because what you've done is you've added two things together, so you get an increase in volume. So this is where the dilution effect thing comes in. But you don't need the dilution formula, because we've got the amounts already. We just need to divide them by the total volume, not the individual volumes. Because they're in the final mixture at the end, the whole volume. Yeah? So rather than dividing by 40 and 50 respectively, we actually divide both of them by 90 because they've been mixed together. Right, so C of HF equals N over V, which is 6.5 times 10 to the minus 3 divided by 90 over 1,000. Don't forget the 1,000. Okay, if somebody can calculate that for me, and then we've got C of F minus is equal to N over V, again, which is 6 times 10 to the minus 3 divided by 90 over 1,000. Okay? Okay, so what's the concentration of HF?
0.0722.
0.0722 mole per litre. And this one?
0.06. Okay, no,
Okay.
How did you work that out?
Because it's 6 over 9, which is 2/3. Okay, so now we've got this. We've got this and this. Yeah, we've got Ka, so we can now calculate the concentration of H3o plus. So the concentration of H3o plus is equal to Ka. So I'll rewrite this so we know where we get this from. Times F minus, and then we're going to divide by F minus, which is equal to 7 times 10 to the minus 4 times concentration of HF, which is 0.0722 divided by 0.0667. Somebody can calculate that for me?
7.58 times 10 to the minus 4.
Got it.
So, just a minute, let's just finish this.
It's not really. How can you be committed to this if you decide to do this?
Yeah.
3.12.
3.12. Now we could do a very quick check here. Could somebody very quickly get me the pKa of HF by taking minus the log of 7 times 10 to the minus 4? Okay? Now, look how close it is. Okay? But if we look at these two concentrations, they're very close. So they're almost 50-50. Remember, at 50-50, the pH equals the pKa. This is very slightly lower. And that's what we would expect because we've got a slightly higher concentration of acid to its conjugate base. Yeah? Very slightly higher. Only very slightly higher. So the concentration of H3o plus will be slightly higher than than it would be under the best conditions, and so this will be slightly lower than that. And so they tie in quite nicely.